All right, good afternoon, everyone. My name is Thijs de Boer. I'm, I guess, the lone phone call in for today. NOAA and Zoom are still not super friendly with one another, so I get to do it that way. I'd like to welcome you all to our August meeting here, and it's one that for the atmosphere team directly targets performance element 2.3.4 in the Arctic Research Plan, which is connected with the environmental intelligence team to support the evaluation of reanalyses, and specifically from the atmospheric perspective, we have a lot of interest in clouds and other controlling parameters, and so this presentation falls right in line with that. And I'd like to thank both of our speakers for speaking to this topic, and I hope we have a really great, fruitful meeting and some interesting discussion. And I'll hand it over to Richard so he can introduce the modeling subteam side.
Hello, my name is Richard Cullither. I'm a co-lead for the modeling subteam, and this topic also has particular relevance to the modeling team. We have a performance element on the systematic improvement of reanalyses in the Arctic, and so I think that these two talks will be related to improving reanalyses in the Arctic, and they have a lot of connection to me. Chelsea will be talking about a new project for NASA for the improved representation of the polar region in global reanalyses. That's called PolarMERRA. And in the second talk, Brant will be talking about ARISE, which was a project that I participated in, which flew out of Eielson Air Force Base in Alaska to gather cloud and radiation data over the Arctic Ocean, and he'll be using that to evaluate reanalyses. And I guess at this point then, should we just begin then with the speakers? So our first speaker today will be Chelsea Parker from the University of Maryland, and NASA Goddard Space Flight Center will be speaking about PolarMERRA.
Hey, okay. I will share my screen here. Okay, I assume everyone sees my screen.
Yeah, we can see it.
Yeah. Okay, so thanks very much for having me. As Richard just said, my name is Chelsea Parker. I'm a research scientist at the University of Maryland, but based primarily at NASA Goddard, although that's basically my home now. I wanted to present today an overview and kind of an introduction of a new initiative that we've been working on that we're calling PolarMERRA. This is very much a group effort, and the work represents everyone listed here. Certainly Richard's on the call and maybe a couple others. So what is PolarMERRA? It's an initiative that brings together the modeling expertise from NASA's Global Modeling and Assimilation Office, GMAO, and observational expertise from NASA's Cryospheric Sciences Lab to assess and improve the representation of polar processes in NASA's modeling system, really in preparation for upcoming and next generation reanalyses. The motivation behind this effort is really, as many of you know, the polar atmosphere is often poorly represented in global models, but yet model representation is really crucial for analysis of polar regions, crucial for forcing other regional and process models, and forecasting, so locally and globally. Additionally, observational data sets for assimilation and validation are often spatially and temporally limited in these remote regions. So improvements really do need to be made on validation and assessment methods. PolarMERRA is hopefully a long-standing project with a number of stages. Stage one is what we've mainly been working on so far and what I'll talk about today. It really involves developing a comprehensive observation validation framework to guide and assess NASA's GEOS model improvements in representing polar processes. Improvements will be implemented for the upcoming GEOS R21C, which is a new and higher resolution atmospheric reanalysis for the 2000s. So this should be coming available in 2021 with a product resolution of 0.25 degrees. The future stages of PolarMERRA are stage 2, which should involve a downscaling, replay of atmospheric reanalysis for an even higher resolution product specific to the polar regions. And stage 3, where additional model improvements and advances that are applicable for the polar regions are incorporated for MERRA 3, which is the next generation coupled ocean atmosphere reanalysis. The timeline for MERRA 3 release is 2024 to 2025. As I mentioned, we're mostly focused on stage 1. So as I've said, and we all know, observations are limited in the polar regions. So what we've been doing is developing a validation framework that really carefully assesses limitations and biases of observations and tries to optimize what we really have available across scales in terms of observations to validate the GEOS model in the polar regions. As a first step, we had originally been conducting validations of MERRA 2 as a testbed and baseline for further analysis of the GEOS system. We hope to be developing and maintaining a validation toolkit for current and future model evaluations in the polar regions. Assessments have guided model improvements and changes. We've only listed a few here, but some important ones to note is that there's been improved topography and resolution, implementation of new physics parameterizations, and changes to surface classifications. Additionally, there has been quite a notable change to the assimilation system since that system that created MERRA 2. So these include transitioning to hybrid 4D and VAR, introducing all sky radiances, and assimilating additional datasets. We do want to highlight that further changes to the model and data assimilation framework will be guided by validations. So we wanted to present some snapshots of the analysis we've done so far and highlight the way we're approaching this assessment and model changes. We have been focusing on both poles, but today I'll be showing the Arctic, given that this is IARPIC. We're looking here at annual surface air temperature over the Arctic Ocean from 1979 to 2017, as represented by a range of reanalyses in the colored lines, and satellite observations from AIR's AMSU in black and the Intersatellite Cloud Climatology Project in with the black dotted line. What we can see is the series shows a general trend of warming over the time period of nearly 1 degree per decade. However, there is clearly a spread in the reanalyses, with some that are typically warmer and some typically cooler. MERRA 2 in pink and red are systematically warmer than the other reanalyses and observations. To look more in depth at the seasonal cycle and understand the bias, here we're looking at analysis of the difference in Arctic near surface air temperatures over 2009 to 2015 from MERRA 2 and in situ drifting sea ice mass balance buoys. The key takeaway here is that the blue and red bars show that in the winter to spring months, so months 11 to 4, both MERRA and MERRA 2 showed a positive or warm bias compared to the ice mass balance buoys. The figure does show a general improvement from MERRA to MERRA 2 to be more in line with the buoy data, but the positive bias still is very apparent in MERRA 2 and definitely warrants attention given that surface temperature is a key variable driving ice mass balance. So getting this atmospheric variable right is really imperative. Analysis has suggested that the biases in MERRA 2 may be driven in part by radiative flux parameterization and the fact that there are limited polar observations to be assimilated. So we're focused on examining the changes to the model since the configuration that produced MERRA 2, and we've been really focused on what that means for the polar regions. When I say the candidate system, we're referring to the current GEOS model configuration that will likely be used for the R21C reanalysis product and potential further PolarMERRA specific products. So here we're looking at different plots of variables from the most recent candidate model system minus the variable from MERRA 2. On the left, we can see that over the most recent winter, there is a decrease in absorbed long-wave radiation. So that's very much clear in blue, particularly over the Arctic Ocean and the main sea ice region. And this is as a result of the new implementation of the RTMG long-wave radiation parameterization and improved cloud microphysics. The figure on the right shows a concurrent decrease in the 2-meter air temperatures over the Arctic Ocean. Again, you can see that in blue, suggesting that there's a reduction in the winter warm bias that we found and shown in the previous slide. So if we turn our attention to moisture and precipitation, we have begun to examine important turbulent fluxes. And here we're looking at evaporation from MERRA 2 minus that derived from AIRS, the atmospheric infrared sounder. So this was over the Arctic region in 2012. The figure suggests that MERRA 2 overestimates evaporation, particularly over the central Arctic and sea ice. You should be able to see that quite clearly in the predominant red colors. This evaporation bias could be contributing to biases in atmospheric moisture content and precipitation, and also might be affecting the energy budget. So indeed, precipitation phase, as rain or snow, and the magnitude and timing of that have significant implications for sea ice evolution and ice sheet mass balance. And our estimates and representation of polar precipitation through models are really key for constraining mass balance and our understanding of the energy budget. Comparisons with observations have suggested that MERRA 2 overestimates precipitation, both as snowfall and rainfall, and across both poles. So the figure we're showing on the right highlights the difference between the mean snowfall rate aggregated from CloudSat swaths and the snowfall rate represented by MERRA 2. So over the 10-year period, 2006 to 2016, in the Arctic, MERRA 2 overestimated the snowfall rate, as you can see in the predominant blue color. From the model perspective, there has been some development to address these precipitation issues. So again, we're looking at difference plots of the candidate system minus MERRA 2. And on the left, we can see a predominance of yellow to red colors, demonstrating there's been a decrease in the total precipitable water or total water vapor in the atmosphere over the past winter in the candidate system. This change is likely as a result of adjustments to the cloud microphysical scheme. And while this has resulted in some reduction in precipitation bias, particularly over the Arctic Ocean, hopefully you can see that in the yellow on the right-hand figure, but there is still a spectrum of colors and spatial patterns in the figure. So that suggests that the physics changes haven't translated into a total reduction in precipitation. So there is an improved representation of the hydrological cycle overall, but the magnitude and pattern of precipitation and associated complex fluxes still needs to be examined further, which we are doing. So to highlight and put the change in precipitation bias into more context, here we're showing an intercomparison of precipitation over the Arctic Ocean from a number of reanalyses from 2004 to 2005. MERRA 2 is in red and clearly at the high end of the spread. But precipitation from GEO's candidate system is in black. And you can see that the changes to the model physics and framework that we've discussed today have resulted in a significant departure from MERRA 2 with a reduction of the bias, kind of moving the system closer to the mean of the reanalysis spread. We've just picked out some examples today. We are looking at further considerations with moisture and cloud properties, and these have been guiding model improvements. And we've definitely found it to be key to conduct this polar analysis to facilitate targeted model changes at this stage of development before the release of new reanalyses. To summarize, PolarMERRA is an initiative to improve the representation of polar processes in NASA's GEOS model and upcoming reanalysis products. Stage 1 that we've talked about today has been really focused on developing a comprehensive assessment framework with observations and reanalyses to guide model improvements. Since MERRA 2, there have been a number of improvements, including resolution, topography, changes to model physics schemes, and changes to the surface representation. The validations we've been undertaking so far are indicating that these changes have reduced biases, such as in radiation, temperature, turbulent flux, and precipitation. These improvements will be incorporated for production of GEOS R21C, so that's the atmospheric reanalysis of the 2000s at 0.25 degree resolution. Down the road with this project is a dynamical downscaling of GEOS R21C at high resolutions over the poles for a polar specific product from this initiative. And there will be continued model developments and improvements towards MERRA 3, which is the coupled atmosphere-ocean reanalysis. I will leave it there with time for questions, I hope. Thanks.
Thank you, Chelsea. That was really nice. Are there questions?
This is Jack. I have a question.
Yeah.
Go ahead, please.
Yeah, so I was just curious. I mean, one of the problems that you pointed out at the very beginning is there's not a lot of observations. So does it make you nervous that you can say that your changes to the candidate system are better because it agrees with the other models and maybe all the models are still wrong?
Yes, certainly that is something to be very wary of, and that's why we've tried to bring in a number of different observations. So while we do compare to other models and other reanalyses, we try to utilize as much as we can what is available in terms of observations. So with precipitation, we've primarily looked at CloudSat, but we're looking at other things as well. But that's not to say that observations don't come with their own problems. But that's why we've tried to have this kind of multi-pronged approach and really develop a validation framework that takes into account kind of everything that we have.
Right. Well, I guess my question leads to, what observations would really be the most critical to have more of, or is it so what we have at more places, or there's a constant struggle for the Arctic Observing Network and the System Assist, all these different people trying to have an Arctic observatory, but it's still very sparsely sampled, and that's problematic.
Yes, absolutely. And that has definitely been an inherent problem, I guess, for all of us thinking about the polar regions. And certainly just more of everything would be great. But certainly I think precipitation has been quite a problematic feature, both in terms of gathering observations and then comparing for models. So that could be a point to focus on, but there are many things as well.
Do you know if, well, it's early, but is Mosaic providing useful observations in a critical part of the world, or no one's released any of the data yet from Mosaic?
So I personally haven't seen any data yet, but that's definitely been something that's widely talked about in terms of that should hopefully provide a really important tool for in situ measurements over the past year. So yeah, we have been trying to bring in as many in situ observations as we can, and that would be excellent to have additional measurements.
Yeah, it's a really good point. I'll bring up that there are Mosaic observations available on the DOE ARM archive through April, I believe. Okay. So much of the campaign is already available, not so much the processed products, but there is quite a lot to look at, and that might be a good opportunity, along with observations from some of the other surface observatories as a complement to some of the satellite comparisons that you've shown already.
Yeah, definitely.
additional questions?
Yeah, actually, Dave Bailey here. Nice talk, Chelsea. So one of the problems is a lot of climate models have issues with too much rain in the Arctic. And so maybe you said this, but I missed it anyway. I'm just wondering about partitioning into solid, liquid, mixed phase, and how you sort of do that in this process.
Yeah, so there have been changes in the model cloud microphysics, and particularly looking at kind of what you're talking about in terms of ice liquid ratios. And Richard and I have been looking at this a little bit, and it does look like the changes to the ice and liquid partitioning has resulted in an improvement in terms of just reducing overall precipitation, but then, as you said, rainfall specifically. So it looks like it's kind of going in the right direction, but I certainly take your point that, you know, it's still hard to get that right. I don't know if Richard has an additional comment.
Yeah, so in our candidate systems, and going back to MERRA 2, our routine weather forecasting model, we use single moment cloud physics. In our seasonal forecasting system, we have been using a 2-moment cloud system, which has been developed jointly with NCAR, but we've had some issues with forecast skill associated with it. In our forward processing system and in the candidate system shown here, we use the aerosol analysis as a predictor for cloud phase, and so that's affecting the precipitation type as well. So those are just some of the things that we've been working on. We don't anticipate that the next systems will have 2-moment cloud physics for cloud phase and for precipitation phase, but that is certainly something that is being worked on at Goddard.
Thanks, Richard. I mean, one comment to follow up on that. I think looking at the slide that had the seasonal 2-meter temperature biases relative to the buoys, there is a clear, well, I don't know if it's clear, but there seems to be a coherent seasonal structure to some of those biases in MERRA and MERRA 2, and I wonder whether the candidate system shows a similar seasonal pattern, and sometimes that will illuminate, where some of the issues may lie if they are cloud and precipitation related.
I would expect it would. This was temperature differences. So I mean, in the Arctic summer, you expect the temperature biases to go down as everything tends to lend towards the freezing point. And so we do see these very large differences in the winter time. We've done some offline experiments with our sea ice surface representation, and we believe that this is part of the reason why we're too warm. So our surface representation is having some type of contribution towards this too warm. But with the introduction of the new radiative schemes, it's an opportunity for us to look at the whole atmospheric column and decide what is affecting our temperatures and what is not.
Yeah, that was actually going to be sorry, go ahead.
Oh, this is Hazel. I just wanted to let you know that someone has their hand raised in the participant list also.
All right, thank you for letting me know. Feel free to call on whoever that is. I don't see the list here.
Wisla, it looks like
that's Wisław here, Wisław Masłowski, Naval Postgraduate School. I was wondering if I could get some little more information about the last slide, the second phase of dynamical downscaling. I would be interested to find out what kind of methodology and tools are going to be used, and whether this is going to be a fully coupled downscaling or just atmosphere only.
So For this, since it'll follow from the R21C, it will probably be an atmosphere-only downscaling. So the NASA systems have a capability known as replay, in which the variables are able to track the observed analyses through a certain state. And so essentially you can track the model through these observation fields every 6 hours. And you can change the model. So you can go to a much higher spatial resolution model. And that's been done, and you get much better representation of polar low features, but more importantly, for the ice sheet people, there's improved resolution of surface mass balance over the ice sheet with the higher spatial resolutions. So it's a dynamical downscaling in that the full model is used, and it tracks the analysis fields that are produced from this lower resolution or relatively lower resolution reanalysis.
The reason for my question about the coupled versus atmosphere only is that our experience with this regional Arctic system model, we will compare WRF standalone with a fully coupled RASM, including the same WRF, the same physics. And actually a lot of biases would be reduced in WRF related to a more dynamical and more realistic representation of the sea ice conditions at the atmospheric model resolution grid size.
Yeah, so I think that's what we've been trying to target is the very... Thank you, Lisa, for the comment. And Chelsea, thank you for your presentation. I think we're going to move on to the next speaker since we're about halfway through the meeting here. Really great discussion there. So our next speaker is Brant Dodson, and he's going to talk about work to evaluate clouds in the Arctic system reanalysis using ARISE measurements. So Brant, please go ahead.
Hi, everyone. Let me try to share my screen. All right, can everyone see that?
Yep, it looks good. It's not in presenter mode yet.
Right. Come on, here we go. All right, so yes, my name is Brant Dodson. I'm from, let me turn my, where's my thingy? There we go. Uh-oh. Okay, turn my thing on, and there we go. All right, so my name is Brant Dodson. I am from Science. I work at Science Systems and Applications Incorporated, which in turn works with NASA Langley Research Center. So I'm going to be talking a bit about looking at the Arctic using ARISE observations and comparing that with the Arctic system reanalysis. So before I start, Heis, do I need to read off the slide number that I'm on just so you can follow along?
I think I could probably keep up. I've got them open in front of me. So
okay.
Yeah, if you want to say you're switching between them, that's great. But otherwise, I think I probably figure it out.
It should be fairly simple if I forget. So all right, just let me know. Okay, so as y'all are all familiar, we need to understand the Arctic better and be able to simulate it better. And one of the critical abilities to understand past and current climate change and to assess future climate change rests on the ability to simulate and model the Arctic weather and climate. In particular, past and present, we need to examine and improve our reanalysis capabilities. And one of the specific components that I've been looking at are low-level mixed-phase clouds, boundary layer clouds, 1,000 meters or thereabouts and below. They remain a really difficult component of the Arctic system to simulate. So there's been a number of satellite data studies used to try to better understand this issue and hopefully resolve it, or at least reduce the size of the problem. However, the satellites, as great as they are, they can't see everything. And so sometimes you need in situ observations from things like aircraft campaigns. to examine aspects of clouds that can't easily be observed from space. Things like the microphysical properties, certain thermodynamic variables, and so on. So at NASA Langley, we've been using the ARISE data set to test the simulation of Arctic low-level clouds to examine those relationships and to compare it with a reanalysis, specifically the Arctic system reanalysis, to one, understand the amplitude, or the what sort of issues exactly are we dealing with, how serious are the issues, and two, maybe we can understand something about why these disagreements occur. So for those who are not familiar, the Arctic Radiation Ice Bridge Sea and Ice Experiment, or ARISE, quite a mouthful. They conducted 16 flights over the Beaufort Sea, just north of Alaska, during September 2014. We're going to be looking at data from 8 of those flights. So these flights were conducted in conjunction with a series of satellite, no pun intended, a number of satellite overpasses looking at the radiation using series instruments and so on. And the overall purpose of the project was to try to look at radiation from aircraft level and compare that to radiation observed from space, and try to get a handle on what's controlling what, and better understand that whole aspect of the system. So in the process, a wide range of cloud variables, hydrometeor variables, thermodynamic variables, and radiative flux observations were collected in the process. So I am more interested, not so much in the radiative flux aspect, but more looking at the relationship between clouds and their thermodynamic environments that they occur in. So we're going to be looking at the relationships between cloud water, temperature, specific humidity, and relative humidity as observed by ARISE. And so we'll then be comparing the observed relationships with those simulated by ASR. So briefly, the Arctic system reanalysis, the second version of it, for those who are not familiar, ASR is a modification of polar WRF, that the weather research and forecasting model. And the goal of ASR was to refine the representation of the Arctic during a period of rapid change, right? The Arctic is one of the most rapidly changing places on Earth. So the modifications made to polar WRF to create ASR were all made with the goal of improving the Arctic representation. And so that makes ASR an ideal candidate for evaluation using ARISE data. So we examine ASR, both ASR data taken both along the ARISE flight tracks that occurred during the field campaign, and also look at just the general statistics of ARISE over the entire Beaufort Sea domain. And just I want to mention that because the ARISE collects data every second or so in its flight, we need to do some averaging of the ARISE data to remove the what would be sub-grid scale things from an ASR's perspective, to conform the ARISE data to the ASR grid. So I don't have much time, I guess, to get too into the weeds here with the results. So I'll just give you a general overview of 4 key results that we found in doing this work. The first result is that ASR lacks both cloud water and the favorable conditions to produce clouds with lots of cloud water, or juicy clouds, quote unquote. So we started off just trying to understand, well, what sort of errors, what are the size of the errors in ASR, what are the things that we need to try to better understand and resolve. So to do this, we examined the grid scale PDFs of cloud and thermodynamic variables to detect any systematic biases in ASR. And it became quickly obvious, looking at, you can see them there on the left, became quickly obvious looking at these, that ASR only produces about 25 to 50% of the observed mean cloud water, 25% along the flight path, and 50% over the entire Beaufort Sea domain. So the pressing question for what the rest of what I talk about today is why the lack of cloud water in ASR. And one thing that was also striking immediately looking at these PDFs is that ASR turns out to be about 2 degrees warmer and about 5% drier in relative humidity than observed. So that tells us pretty quickly that at least one of the likely causes of the reduced cloud water is that ASR just is not producing the conditions that are favorable for cloud formation and juicy cloud formation. The second result is, so, you think that these clouds looking over the Beaufort Sea during the late summer, early fall would be, you'd be looking at mixed phase clouds, but neither ARISE or ASR really found all that many mixed phase clouds. And you might think that, well, if ASR has difficulty simulating clouds, maybe it's because that, well, mixed phase processes are really difficult to simulate and to parameterize in reanalysis and models. So, maybe it's just the mixed phase parameterization that's going awry. But the main issue with that argument is that, one, ASR does not produce, it produced almost no cloud ice, as you can see in these vertical profiles I'm showing on the left. And two, it was difficult for ARISE to find a lot of cloud ice as well. It didn't observe much cloud ice. So the disagreement isn't an issue with ASR not being able to simulate mixed phase cloud processes well, because there weren't really any mixed phase clouds. And one other thing I want to note, when we're looking at this, we also found that ASR tends to not produce cloud water at all above about 500 meters or so. It's okay below 500 meters, but not so much above 500 meters. So we didn't really look into, what sort of errors in boundary layer processes might relate to this. That's probably an involved project, but it could be something of major importance to look into in the future. The third result is that turns out that even when ASR produces conditions that are favorable for cloud water, it still lacks cloud water. It doesn't produce all that much of it. So as you recall earlier, one factor is that ASR is biased towards warmer and drier conditions. So you might think, well, that's the primary cause. And we found that that is a significant cause, but we wanted to look at, well, what about favorable conditions for cloud water formation in ASR. So what you're seeing here on the left, I know this graph's a little busy, but basically we're conditionally sampling cloud water, both observed and simulated by various thermodynamic regimes, collections of temperature, relative humidity, and specific humidity, so that we can better understand the relationships between clouds and their environment. So the gist of what you're seeing in the left column, the ARISE observations, is that the observed juicy clouds tend to form in conditions of low temperature, low specific humidity, and high relative humidity. So temperature and relative humidity are not too much of a surprise. Specific humidity was interesting in that simply providing more water vapor in order to condense into clouds doesn't seem to be enough to produce juicy clouds either in the real atmosphere or in ASR. It's more related to the processes that convert water vapor into cloud water. And so ASR struggles to produce these juicy clouds in low temperature, low specific humidity, high relative humidity conditions, especially along the flight track. It's a bit better when looking at the full Beaufort Sea domain, those figures you can see in the far right column, but still there's a significant underestimate of cloud water even in these favorable regimes. And so this is another major contributing factor to the lack of cloud water in ASR. The fourth and final result I want to discuss is that we were trying to address a question that might immediately come to mind when talking about aircraft data collecting campaigns, is that, well, the aircraft can't fly everywhere, you know, can't see nearly as broad an area as a satellite can. So how does the limited coverage of an aircraft really affect the values collected from the aircraft and these comparisons that I was showing? And in particular, what if the aircraft just during the actual ARISE campaign, what if the aircraft just by chance had flown in regions where ASR and ARISE happened to just disagree, you know, just by chance? So we can't go back and refly the ARISE campaign itself, of course, but what we can do is simulate a virtual ARISE campaign, flying a virtual aircraft or you know, aircraft on several flights through ASR. And so we conducted a Monte Carlo random sampling experiment in which we run a number of virtual ARISE campaigns within ASR, randomly fly the aircraft in different locations at different times to try to understand how does this limited sampling issue affect our results. And so you can see on the left, there's a bunch of statistics that we use to look at this. Don't really have time to get into that, but the takeaway here is that there are two things that combine to cause that, you know, 25% cloud water along the flight track versus the 50% for the entire domain. And part of it is that these juicy cloud thermodynamic regimes are relatively rare, and the aircraft is by chance is likely to miss them. And second, there's enough variability in cloud water, even in these favorable regimes, that sometimes the aircraft just going to miss the juicy clouds, even if it is in the correct environment. So this information could be used to better understand this type of comparison, and maybe even in the future help in designing future aircraft and other in situ experiments to try to better compare the reanalysis with the observations. So how much time do I have left? Can you let me know really quick?
A couple minutes maybe, so we have time for questions and a little bit of
all right.
discussion. Yeah.
All right, so I'll just mention briefly that one other interesting thing that we found is that ASR also produces juicy clouds, you know, large cloud water values in conditions of high temperature, high specific humidity, and high relative humidity. And these regimes are simply unobserved by ARISE. So with the ARISE data, we can't really tell, are these regimes simulated in ASR, are they realistic? Do they exist in the real atmosphere? If they do exist in the real atmosphere, do they also produce juicy clouds? I would think so, you know, just noodling over it, but we don't know from the data that collected. So that's another interesting thing to think about, particularly when maybe even designing future aircraft campaigns. So just a couple of conclusions from this. So we've examined how ASR, well, we've used the in situ data from ARISE to explore this lack of cloud water in ASR, and able to find out that it's from a combination of both a lack of favorable conditions for juicy cloud formation and insufficient cloud water produced even when you have good conditions. So this is just looking at, of course, at one reanalysis we think, you know, Patrick Taylor and the rest of us in our group think that this sort of analysis can be really useful for examining other reanalyses to try to better understand and better represent Arctic weather and climate. And finally, our future plans in my group are looking, I mentioned earlier that I've averaged out the subgrid scale information, but we're going to look more at that subgrid scale information and to see if we can test some of the assumptions made in the microphysical parameterizations about, you know, the distribution of cloud water within grid cells, distribution of humidity, and so on. So that's all I have. Thanks for listening.
Great, thank you very much, Brant. Are there questions or comments? One comment I'll make is that I think your question of the representativeness of the measurements is a really good one to ask, and of course a difficult one to answer. But you know, there are observatories on the northern Alaskan coast that might be leveraged for answering some of the questions about the regimes under which we see the juiciest clouds. And I tend to agree with you that I would not be surprised if a lot of those juiciest clouds come with warmer conditions, with, you know, cyclonic events that are coming up from lower latitudes across Alaska. But it would be a really interesting problem to go after.
Mm-hmm.
So this is Jack. I had another question, or maybe it's a comment. Have you thought about looking at the April campaign during PolarCat? I think it was 2008, where there was a lot of airplanes in Fairbanks. I know the DC-8 and the NASA King Air were encountering quite a few mixed phase clouds, and I think DOE was really targeting clouds as their major focus on their part of the campaign.
Mm-hmm.
So yeah, it's a little bit earlier if you're interested in the changing Arctic, but you could still see how the model did, and I think there were more juicier clouds around at that time than it sounds like ARISE was able to find.
Right. So my group of certainly we've discussed using or looking at other campaigns. So we're using the RISE campaign as kind of a test study for this sort of examination. So, you know, if this turns out, and we seem to have a fair bit of success with it, so certainly this opens the doors to looking at other field aircraft campaign data, which is important because, you know, they're much more limited in availability than satellite data and, you know, other data sources.
Another campaign you might consider, which is closer to the 2014 window, is the ACME 5 campaign that DOE conducted over the summer of, I believe it was 2015, but I should double check, where they flew over, not so much over the ocean, but more over the Alaskan land surface for the whole summer.
All right.
Similarly, I think that the French did a big campaign, maybe even more recently than that, where their focus was on trying to document impacts of shipping on just air quality and pollution, but I think they had an aerosol cloud component as well. That'd be on the other side, but the model shouldn't care.
So, hi, this is David Bromwich here. I'd like to make a small number of comments about this.
Please, go ahead.
Yeah, so thanks very much for the presentation. The situation with reanalyses, it's important that to discriminate between the variables which are assimilated, which are the things like the temperature and the relative humidity and the winds, and those that are actually predicted by the model physics, which are the hydrometeors, for example, the clouds, and as a result, the radiation, the partitioning between cloud liquid water and cloud ice. So these are very much dependent, the things we're looking at here in general are very much dependent on the cloud microphysics. So with the Arctic system reanalysis, it is a older system these days. It was a single moment microphysics scheme, as we've heard about already. And the work that's being done here and in both poles actually with the Arctic system reanalysis is designed to get across a wide range of circumstances to help us understand this partitioning between cloud liquid water and cloud ice, which is a very challenging modeling problem. And we are, like NASA, preparing a new version of this, of our Arctic system reanalysis. And in this context, the new two-moment microphysics schemes will be particularly important. And we'd like to start with the mosaic year, that's fall of 2019 to fall of 2020, which has a large number of in situ observations from that drifting site across the Arctic Ocean, in particular the clouds and the radiation. And I think I'll stop there.
Thank you, David.
So I would like to ask a question to David and other members of the group. So I've shown this analysis using cloud water from ARISE and ASR, but ARISE also collected other cloud variables, microphysical variables, things like number concentrate, hydrometeor number concentration, total volume, and from that you can derive mean radius. So I can run a analysis similar to what I've shown you, but using those variables and even compare them with cloud water. I was wondering for the modelers, would that type of thing be really useful for you? Is that the kind of thing that you would like to see?
I think the answer is I need to think about that.
Okay. All right. Let me know.
Yeah, I will.
All right, any last comments or questions?
Oh yeah, just quickly to me, this is Hailong. If you're using a double moment microphysics, the correctly simulating the cloud drop number could be very challenging, since lots of aerosols are from the lower latitude rather than within the polar WRF domain. So if you have observations of those drop numbers, would be very useful to me, I think.
All right.
Yeah, good point. Thank you.
Thank you.
Thank you, Helen.
Yep.
This is Richard. I think that's exactly right. And that's our issue with using two-moment microphysics in the Arctic, is that we don't have enough information about the aerosols up there.
We as a first cut at this, we can do substantially better than using mid-latitude aerosols. And there are some climatologies of aerosols anyway for the Arctic, which are based on NASA data assimilation, I think. And there are some microphysics schemes, the Thomson-Eidhammer microphysics scheme, which is also available in WRF, that uses these climatologies directly. So there are some, but you're right, ideally you would like to have a prediction of the aerosols to go with the microphysics scheme.
Very good. Well, this might be a very nice segue into planning for the next Arctic research plan. If more aerosol information is required, that would be a very good thing to try to make sure that we include in the plan. I think we're moving towards the point of the meeting where we'll wrap up, and I'd like to give Richard an opportunity to just speak on behalf of the modeling sub-team, maybe introduce what you're doing next month, Richard.
So we actually have a meeting this Thursday at 3 o'clock, which is joint with the Sea Ice Collaborative team, which will be looking at model contributions to the this year's Sea Ice Outlook.
Excellent, thank you. On the atmosphere side, our next meeting is going to be focused on collecting input from the community, which is all of you, on activities that have been undertaken for reporting. One of the most exciting meetings we have all year. But we have our obligations to track as much as we can what has been going on in the Arctic research community, and then report back through IARPIC on those activities and demonstrate progress on the plan. So I would encourage everybody, to the extent possible, to respond to us as the team leads, or to IARPIC generally. There was an email from Meredith LaValle earlier today about reporting back on ongoing activities, so that all of those efforts can be accurately tracked and represented in our reporting documents to Congress and others. So please do consider how your work has perhaps contributed to progress towards the current Arctic research plan. I think with that, I'll just briefly poll the other team leads. Have we forgotten anything? Are there other things we should be discussing, or Hazel as well? Anything that we forgot today?
Just a reminder to everyone that thanks for joining us today, and the notes from this meeting and the recording will be posted sometime later this week. So if you need to reference back to anything that was discussed here.
Yeah, very good. Thank you, Hazel, for that reminder. Any other last comments? All right, if not, thank you everyone for joining us today, and thank you to the modeling sub team for joining us as well. And we hope to continue making progress on the reanalyses and their ability to represent clouds and other things. So we hope to have additional meetings in the months ahead on similar topics, and we'll make sure to keep everybody in the loop on when those might be happening. So thanks for joining, and we hopefully will see you again very soon. Have a good day.
Thanks, man.
Thanks, guys.